Okay, folks, how we doing? Last lecture video on chapter 4. So let's go through those learning goals. So from the previous two videos on acid and bases, as well as precipitation, let's talk about what we did there. So from the acids and bases video, I want you to know the list of strong acids, strong bases, weak acids, and weak bases we discussed in class. So know those acids and bases. So be able to balance an acid-base reaction as well as perform stoichiometry calculations on an acid-base reaction. And one thing that I want to take note of, previously in our stoichiometry calculations, you were often given a mass of something to do the stoichiometry calculation. So you use the molar mass to then convert it to moles. Well, with these acid-base reactions, and as we'll also see with the precipitation reactions, you're usually going to be given a volume and a molarity. And when you have a volume and a molarity, you don't need the molar mass. That gives you the number of moles directly. Okay, so just keep that difference straight. So understand the components of a titration reaction. You're eventually going to do a titration reaction in your virtual lab. So hopefully that will round off that discussion nicely. Okay, so know how to predict. So that's let's see. That's just about everything for the acid-base stuff. There's one more thing here. Know how to write a net ionic equation for any precipitation or acid-base reactions. So be able to do those net ionic equations, okay? And know how to predict the correct products and the correct phases in a precipitation reaction given the solubility rules. So you don't have to memorize the solubility rules. They will be given to you, but you still have to know how to use them to predict the right products and predict the right phases. Okay? And of course, just like in the acid-base reactions and doing stoichiometry, know how to do stoichiometry calculations with precipitation reactions. And again, typically in these types of reactions, these solution reactions, right, where you take a beaker of solution A, mix it with a beaker of solution B, you're going to have a volume and a molarity. So that negates the need for molar mass, but still pay attention to that, okay? And in this very last video, I'll be describing these last three learning goals, all around and about oxidation and reduction reactions. Okay, let's do it. So here we go. Oxidation reduction reactions, or what we often like to call in chemistry, let's see here, pen, black ink, thank you very much. It was on the text. We often call these redox. And my abbreviation for reaction is RXN. Okay, so redox reactions, or reduction oxidation, or oxidation reduction. Okay, so here's two really important examples of redox reactions. So this one that I'll talk about on the right here, this one is kind of the obvious example of metal being rusted, right? We have iron metal reacting with oxygen, and this lovely orange rust color is iron oxide. So that's an oxidation reduction reaction, okay? There is a redox reaction going on when you have metal reacting with oxygen. In fact, we even say that this metal is being oxidized. You probably heard my son running by me. I'm not going to stop recording. I'm just going to let it go. So this metal, it's literally being oxidized to make iron oxide. Okay, so that's a redox reaction. Another reaction that's not as let's see, what's the best way to put this? So for beginning chemists like yourselves, typically students don't think of a combustion reaction, right? This is methane plus oxygen to make CO2 and water. Combustion reactions are oxidation reduction reactions or redox reactions. And this is actually a really cool picture from the book showing a rocket engine being tested at the Jet Propulsion Laboratory. So this is some methane being burned in oxygen to make that blue flame, okay? So this is also a reduction oxidation reaction. So obviously redox reactions are super important in chemistry, okay? So how do we identify them? Well, the first thing we have to be able to do is determine the oxidation state or the oxidation number, okay? And oxidation state is a chemical property, okay? So just like density is a physical property, or the state, like solid, liquid, gas, those are physical properties. Oxidation state is a chemical property, and it tells us the likelihood of something to react, okay? So you have to know these rules, and you have to be able to put together the oxidation state or the oxidation number of any atom in a chemical reaction. So here's how it goes. Any atom in its elemental form always has an oxidation state of 0. So you have to know when is something in its elemental form. Well, sodium metal, for example, or for that point, any metal on the periodic table that is a metal. Or I should really say any solid on the periodic table that's a metal, right? So like iron, metal, or gold, or excuse me, that's silver. Gold is Au, okay? Right? Any of these things that are in their natural elemental form will have an oxidation state of 0. So that also includes O2 gas, as well as N2, H2, F2, Cl2, Br2, etc. Okay? So now, what about when you have a monoatomic ion, so a single atom that's an ion? Well, the oxidation state is the charge of the ion. Okay? So for example, sodium plus would have an oxidation number of +1. Chlorine minus, so chloride, would have an oxidation state of -1. And now this is also why we often write the charge like this, 1 plus, so that we can write the oxidation number as this, +1. Okay, so that's why we see those things switched up. Okay, so as it turns out, fluorine, specifically fluorine, is always -1 in a compound. Okay, except for, of course, F2 gas, because that's the elemental form of fluorine, so that would be an oxidation state of 0. However, in this HF molecule, it's -1 for the oxidation state. Same in this PF3 molecule. It's also got an oxidation state of -1, right? And so you might think, well, what about chlorine? Chlorine is right below fluorine on the periodic table. It should behave very similarly, and it does. And most of the time, chlorine has an oxidation state of -1. However, you're going to hear me say this over and over again. Chemistry is the science of exceptions. So fluorine rarely, if ever, has an exception. It's always -1. Chlorine, on the other hand, has some exceptions. And so we have to be able to deduce what the charge on our chlorine is first, to then go ahead and confidently say that it's a -1 oxidation state. Okay, we'll see examples where that comes up. But I'll also remind you, just like F2 gas is 0, then so too is Cl2 gas. So got to keep these rules straight, okay? So oxygen, oh, I just realized my exceptions are, and then it got cut off. Exceptions for oxygen are hydrogen peroxide. So let's talk about the main rule first. Okay, we did fluorine. So oxygen is almost always -2. for its oxidation state, because its charge in compounds is almost always 2 minus, right? So for example, in water right here, this oxygen has an oxidation state of -2. This CO2 has an oxidation state of -2. However, the one exception I want you to know for oxygen is hydrogen peroxide, okay? So in hydrogen peroxide, it looks like this, HOOH. That's how all the atoms are bonded together. And each oxygen in a peroxide is -1. So that's the exception. And the reason for that is because you have -1 and -1, but each hydrogen is +1 and +1. So that's why this peroxide has that exception. And what it means, so think about this, if oxidation state is a chemical property, because the oxygen in a peroxide is -1, but oxygen in all other compounds are -2, this means peroxides react differently than other oxygen-containing compounds, okay? And we know that because it has a different oxidation state. It's a different chemical property. And then the last rule here, hydrogen in covalent compounds is always +1, right? So this hydrogen peroxide compound is covalent. So these hydrogens have to be +1. So that's why those oxygens are -1, because all of those oxidation states have to add up to 0 in the case of hydrogen peroxide. But in other compounds, the oxidation states all have to add up to what the charge is. And we'll see an example of that, okay? But on this hydrogen example, right, in H2O, each hydrogen is +1. In this HCl, each hydrogen is +1. And in this NH3, each hydrogen is +1. And keep in mind, okay, keep in mind that the charge and the oxidation state sometimes are the same, okay? But sometimes they are not. So we have to recognize when they are the same and when they are not. So you want to remember these rules and be able to go through some examples, which I'm going to do next. All right? So carbon dioxide. So assign oxidation states to each atom in the following molecules. So we have the carbon and the oxygen. Okay. Well, if we back up on the rule here, oxygen compounds are -2. Exceptions are peroxides. This is the only peroxide I'm going to give you in this class, H2O2. I know this looks confusing because you might think, well, this is CO2. That kind of looks like the peroxide. It's not. It's not because it doesn't have that bonding pattern of COOC. Okay, there's only one carbon there, so it can't have that bonding pattern. So each oxygen here is -2. Carbon dioxide is a neutral atom, okay, so it doesn't have a charge, or neutral molecule. It doesn't have a charge, so everything has to add up to 0. Okay, look, I've got 2 oxygens, and they're each -2. So I can set up this little algebraic equation to solve for what the carbon has to be. And so if we go through and solve this, we would learn that each carbon, or the only carbon that's in CO2, is +4. Okay, so these are our oxidation states in carbon dioxide. Okay, let's do SF6. All right, so we remember from the rules that fluorine in compounds is always -1. Okay, so that's -1. And again, I'll set this up as an algebraic equation, but hopefully when you get enough practice on this, you can just do the algebra like that. Okay, so SF6, neutral compound, okay? So everything has to add up to 0. So I know that there's 6 fluorines, and each one is -1, okay? And quickly doing some algebra here, that means the sulfur has to be +6 for the oxidation state. Okay, so what about H2O2? Well, I just did that one. So this is our hydrogen peroxide. So each hydrogen is +1 and each oxygen is -1. And we would also deduce that because, again, it's a neutral compound. Everything has to add up to 0. There's 2 hydrogens, and they're each +1. And there's 2 oxygens, and they're each -1. So that all checks out. Okay. So now what about this NO3? And I want you to pay especially close attention to this. NO3 versus NO3 minus. These are 2 different chemical compounds. One is an ion, the other is not. Okay? That's big. Just that little minus charge makes these 2 molecules very different. Okay? So let's first do the NO3 neutral. Okay? So we know it doesn't have a charge, so it's all the oxidation states have to add up to 0. This is not a peroxide, so each of those 3 oxygens are -2. So that means in NO3, the nitrogen has to be, you guessed it, +6. Okay? Well, what about nitrate? Okay, the nitrate ion. Okay? Well, everything has to add up to -1. This entire NO3 minus is a -1 charge. So now we're going to actually start to see the bigger picture. Why do these polyatomic ions have a charge? And the reason for it is, well, you have 3 oxygens, and they're each -2. Okay? So, but for this relationship to be satisfied, right, if I do the algebra here, we would find that this nitrogen has to be +5. And that is why this nitrate is -1. Because a nitrogen with the +5 oxidation state is different than a nitrogen with a +6 oxidation state. They are chemically different. They do different chemical reactions. All right? Cool stuff. I'll give you another example. Why is SO4 2- always 2-? Well, if we look at this thing, right? Let me write that so it's a little bit more clear. Okay? Well, the whole thing is -2. The whole ion has a -2 charge. There's 4 oxygens, and each have a -2 charge. So what's the oxidation state of my sulfur in sulfate? Well, it would have to be +6. Whoa, cool. The same thing we saw with this SF6 compound, right? Pretty neat, okay? So this is why sulfate, SO4, has to be 2-. All right? And we could go through all of the other polyatomic ions. You know, why is phosphate PO4 3-? Why is acetate CH3COO-? Okay? It's because of the oxidation states. Those are the chemical properties of those atoms in those molecules. All right. So be able to come up with oxidation states for any compound. You might need a lot of practice doing that. I expect you will, just like everything. Okay? But I'm going to move forward and talk about how we use these oxidation states to do chemistry. All right? So here's a reaction. Sodium metal plus chlorine gas makes sodium chloride. I would love to do this reaction for you. This is a reaction we do in the lecture hall, and it's super awesome. This is quite a violent and explosive reaction. So you should look this up on the YouTubes. I don't have a little video ready for you, but look up sodium metal and chlorine gas. It's a really violent reaction. Okay? So if I were to go through and do the oxidation state of each atom in this reaction, we know sodium is in its elemental form, so it's 0. Chlorine, Cl2 gas, that's its elemental form, so that's 0. And now NaCl, we know that sodium in sodium chloride is a cation with +1 charge, with 1+ charge, rather, right? So meaning its oxidation state is +1. And we know chlorine in sodium chloride is 1- charge, so it has a 1- oxidation state. Okay? So now let's look at what happened to the sodium. So in going from sodium metal to sodium plus, its oxidation state increased by 1. And going from chlorine gas to chloride anion, its oxidation state decreased by -1. So what is happening with this thing? Okay, well, we have this really famous mnemonic, right? Oil rig. Oxidation is a loss of an electron. Reduction is a gain of an electron. All right? So if we look at what happened to the chlorine, in order to go from 0 to -1, it would have had to gain an electron. I'm going to say plus E minus, and I'll say E minus is our symbol for electron. Okay? Right? Because to have a decrease in its charge, it had to have 1 extra electron. That's how it became -1. Well, then what about sodium? Well, for sodium to go from 0 to +1, it's tempting to say, well, it had a proton added to it, but it did not. That would be a nuclear reaction if we forced sodium to take on a new proton. And I'm not talking about an H+ acid proton. I'm talking about a proton in its nucleus. That would be a nuclear reaction. We don't do those. It takes a very extraordinary set of conditions to add or take away things from a nuclei. So when you go from 0 to +1, that's because it lost an electron. So I'm going to say -1 electron, and that's what makes it +1. So now we note that if oxidation is loss of electron, then sodium has been oxidized. Okay, sodium lost an electron, so it has been oxidized. Reduction is gain of an electron. So we can see chlorine gained an electron, so it is reduced. Okay, and now what we have to think of is, I like to call this, making action verbs out of these. Okay, so if sodium is oxidized, who did the oxidation? Well, chlorine did, right? Sodium is not going to auto-oxidize. It's not going to oxidize by itself. Something has to oxidize it, and that's the chlorine. Okay? On the other hand, chlorine is reduced. It's not going to get reduced by itself, so sodium had to do the reducing. So when we identify which species is oxidized, we note that the other one had to be the oxidizing agent. When we note that the other species is reduced, we note that then the opposite one had to be the reducing agent. So think about that in terms of like an action verb. If this thing is oxidized, who did the oxidation, right? And that's why we call these redox or oxidation reduction, because where there's an oxidation, there's always a reduction, and where there's a reduction, there's always an oxidation. Okay? Another easy way to remember, so this is oil rig. Another easy way to remember for at least the reduction, which one is reduced, look what happens to the oxidation state of chlorine. It goes from 0 to -1. It was reduced in number. That's precisely why we use that word, reduced. Okay? So lots of ways to get around this. Whatever is the easiest way for you to remember oil rig. There's also another acronym, Leo says GER. Leo says GER. I don't know this one very well. So what is it? I guess loss of electrons is oxidation. Oh, now I get it. GER. Ha 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 ha. Loss of electrons is oxidation. Gain of electrons is reduction. Okay, so I like oil rig better, but if you like Leo says GER, that's okay too. Okay, so let's keep going. Okay, so here's an example. Identify the reducing agent and the oxidizing agent in the following balanced reaction. I'm just going to go for it. I'm going to walk you through how I do it. If you want to pause the video and give it a shot for yourself, then go for it. Okay. So first thing that I'm going to do, though, is add up the oxidation states. And I'm going to write the oxidation states in red here so I know what they are. Okay. So for example, I know each hydrogen has to be +1. I know each oxygen right here has to be 0 because this is O2 gas in its elemental form, right? Over here, I know now this is now a compound. This is oxygen in a compound. So each oxygen has to be -2 over here. And now in water, each oxygen is still -2 and each hydrogen has to be +1. So the only thing that I have left to figure out are the carbons. Okay. So over here in carbon dioxide, 2 times -2 is -4. So each carbon has to be +4. Okay, so I'm going to try to indicate which is which. Okay. And then now on methane, each hydrogen is +1. There's 4. 4 times +1 is +4. So that means each of these carbons have to be -4. And now what I want to do is identify each element or each atom that underwent a change. So carbon definitely changed, right? It went from -4 to +4. Okay? And let's see. So the hydrogens didn't change, so I'm not too worried about the hydrogens. And yes, aha, each oxygen went from 0 to -2, both in water and in carbon dioxide. Okay, so what happened? Well, for carbon, to go from -4 to -8, let's think about what has to happen. So it's already negatively charged. So for it to go positive, it's not being reduced, right? The number's not getting smaller, the number's getting bigger. So that means that it had to be oxidized. And how I know it had to be oxidized is because to go from -4 to -8, that's like saying -8 electrons. Okay? So that's a loss of electrons. So I would say it's not just the carbon in methane, it's the entire methane. Methane is oxidized. I'm not going to identify what's the oxidizing agent yet. Let's just keep going through this thing. Okay? And so now oxygen went from 0 to -2 in both of these compounds, right? And then consider that we really have, 4 oxygen atoms in total, right? 2 times 2 is 4. Well, here's 2 of them, and then here's 2 of them. Okay, so we accounted for all of them. And so that means for this to happen, each oxygen had to gain 2 electrons to go from 0 to -2, and there was 4 of them in total, so that's actually an exchange of 8 electrons, which is kind of cool that we could account for all of that. If you didn't see the number 8, if you're not there yet, that's okay. The big important thing to note is it went from 0 to -2, it's being reduced, okay? So O2 is reduced. And note, we always say this with respect to the reactants. We're talking about what's happening with the reactants. Okay, so if methane is oxidized and O2 is reduced, that means O2 is the oxidizing agent and methane is the reducing agent. And here's another really cool thing, some kind of common sense. It's not quite common sense yet, but we'll call it chemistry common sense, which means it's only common sense after you've been studying chemistry for kind of a long time. Oxygen is always the oxidizing agent. Makes sense, right? I should say 99.9% of the time, okay? So that's how you know you did this correctly. don't just assume oxygen is going to be the oxidizing agent. You know, walk through this and make sure you get it. But yes, in a chemical reaction where there is O2, 99.999% of the time, oxygen is the oxidizing agent. That's called chemical intuition or chemical common sense. Okay, let's go back for a second. Check this out, right? Iron plus oxygen makes iron oxide. What do you want to bet in this reaction? Oxygen is the oxidizing agent. It is. Work it out for yourself. You should try this example out, right? Put together the oxidation states of iron and oxygen and so forth and prove to yourself that oxygen is the oxidizing agent. Okay? It doesn't have to be the only oxidizing agent in the world, but certainly in a chemical reaction with O2, you guessed it. You know what it's going to be. Okay. So now let's move on, moving forward. And we're going to talk about how we balance these redox reactions. Okay? So there's a special way we have to balance these reactions. Not only do we have to balance the atoms like you've done previously, but we also have to balance the charges, and thus we have to balance the electrons. Kind of like how I came up with this 8 and 8 off the top of my head. I'm now going to work out how we can come out with that number. I just presented these very quickly, 8 and 8, but there is an organized way in which we can come up with this and balance those electrons. So the first thing we want to do is, so this is called the half method, and we're going to break this reaction down into two half reactions. Okay? And we break them down into the half reactions based on the atoms. All right? So this one is pretty easy. So I can see I've got a Ce4 plus and a Ce3 plus and a Sn2 plus and a Sn4 plus. So that's going to be pretty easy to break this one up into its two halves. Okay? So I'll write this first half like so. And I'm going to drop the phases just to make this a little bit easier to write. Okay? And we'll put the phases back in at the end. And then I'll write this other half, and I'm going to give myself plenty of space here. Okay? And so now what I first want to do is balance the atoms. And when I look at this, I can see that so far it looks like my atoms are balanced. So I don't need to do anything there, right? There's 1 and 1 and 1 and 1, so we're good to go there. The next thing I need to do is balance the charges. And I balance the charges with electrons. So I've got 4 plus, let's write plus 4 on this side and plus 3 on this side. And I can balance these numbers by saying plus 4 minus 1 makes plus 3. So how do I add a minus 1 in a chemical reaction? Well, I can do that by saying plus an electron, right? So when this ion reacts with an electron, it goes from being 4 plus to 3 plus. Beautiful. What about this half? Okay. Well, if it's plus 2 on this side and plus 4 on this side, then I need 2 minuses on this side, and I can achieve that by saying plus 2 electrons. Okay. So now I've balanced each respective half, and I'm ready to bring them back together. And I'm going to bring them back together by adding them. Just like I can add equations in algebra, I can add chemical reactions in the same way. Okay? But what I want to do to balance this is I have to balance the electrons. Okay? So I've got 2 electrons on this side, but only 1 electron on that side. So I'm going to need 2 electrons in total. And the way that I do that is not just by putting a 2 right here. I have to say times 2 of the entire reaction. Get out of here, antivirus. Okay. I have to multiply this entire reaction by 2. And when I do that, okay, we'll say equals, right? I've got 2 of everything now. Okay? So when I recombine these, I want my electrons to cancel. And what I'm left with for this balanced reaction is 2 of these ions, but we would not have ever expected that just looking at the equation. Okay? And we wouldn't have gotten that because we didn't really know what these oxidation states or charges were before. But now we recognize that because the charges and the electrons have to be balanced, we actually needed to have a 2 in front of that to make it work. And now also, if we think about this for just a second here, if we were writing this reaction as is, right, up here, look, it's 7 total plus on this side, 4 plus 3, right? And it's 6 total plus on this side. That's how we know this is not balanced. Straight away, if we looked at that and recognizes that the charges have to be balanced too, we would have seen that it was not balanced. So when we put a 2 here and a 2 here, now let's see what happens. So now I've got 2 times 3 is 6 plus 4 is 10. And over here I've got 2 times 4 plus 2 is also 10. All right? Okay. So hopefully you're feeling okay with this example, because I'm going to do, let's see what's coming up next. I'm going to do a couple more complicated examples, okay? And I'm going to walk you through them. It probably means that this lecture is going to go on for a little bit longer than I wanted it to, but that's okay because we're working through examples, all right? So now let's balance this using the half reaction. However, we were given a new condition. Okay, we were told this is an acidic condition. So in other words, that means that in order for this reaction to be a redox reaction, it has to be in an acidic solution. To be in an acidic solution. And you wouldn't have known that yet, okay, beginning chemistry student. But now we're telling you, okay, we can balance this reaction, but it has to be done in acidic conditions. How are we going to do it? Here's how, okay? We first split it up into 2 halves, and I can base that from the atoms. So like I see, here's an iron half, great, and here's a manganese half. So let's split those up. So I'm going to say over here, iron 2 plus makes iron 3 plus, and maybe hopefully what you can see right away, we need 1 electron to balance that, right? 3 minus 1 gives me 2, okay? And that's it. That one's done. Easy. So what about this manganese half? Okay, so I'm going to write this way over here. I'm going to try to give myself plenty of space. I'm going to drop the phases for now just to make this easier, but I'm going to bring them back in at the end, okay? And so now, let's see, did I give myself a good amount of space? I probably did, and I'm going to shift this whole thing over just a little bit for more space. Okay. MnO4 minus permanganate, right? Okay. So the first thing I recognize with this, there's 4 oxygens on this left side, and there's no oxygens over on this side. So how am I going to deal with that? Well, it's aqueous. Look, aqueous. That means we have water. Water is around. It might not be written in this chemical reaction, but it means we have it and we can use it. And I'm going to use it, and I'm going to say plus 4 H2O. And the reason why I said 4 of them is because I want to balance those 4 oxygen atoms, and I can balance those 4 oxygen atoms by adding 4 water molecules. Well, now we're going to play this back and forth game, because now you might say, well, we've added 8 hydrogens that we didn't have over on this side. And that's true. But This problem told us this has to be balanced in an acidic solution. And so what that means is these 8, 4 times 2 is 8, hydrogens, I can balance by saying 8H plus. Not just 8H or 4H2, I need specifically 8H plus because that makes it acidic. Okay? And now, when I inspect this, I've got 1 manganese, 4 oxygens, 8 hydrogens, and 8 hydrogens. However, what about my charges? Okay, well, on this side, 8 times plus 1 is plus 8, minus 1 is plus 7. So water is 0, 4 times 0 is 0. And manganese is plus 2 plus, right? So its oxidation state is plus 2. So I can balance these numbers now by taking away 5. And the way I take away 5 is by actually saying plus 5 electrons. Okay, so now plus negative 5, right? And that's going to balance it out. Beautiful. So now that I've balanced each half, I can bring them back together. Okay. And let's see, I'll write the iron on top. You know what I realized I also forgot to say on this last problem, but now I'll add it on this problem, okay? This half, right, that's going on, iron 2 becoming iron 3 plus an electron. Look, it's the iron 2 is losing an electron. So yep, you guessed it. This is the oxidation half. So that means, look, this permanganate is gaining an electron. So that means this was the reduction half, okay? Right, I said that in the beginning. All reductions have to have an oxidation. All oxidations have to have a reduction. So when we split these up into the halves, we're really splitting it up based on its 2 respective half reactions. Okay, so now we've written this iron reaction down. Let's write this manganese reaction down. Okay. Plus 8H plus 5 electrons. And that makes Mn2 plus 4 H2O. And hopefully what you can see, I hope you can see this, the electrons ended up on opposite sides, so that's how we know we're good. If your electrons end up both on the same side, you can't cancel them. So you did something wrong. But also, I have 5 on this side and 1 on this side. So the easiest way to balance that is to multiply this entire reaction by 5. Okay? And so I'm just going to write the result down directly. When I do that, I get 5 iron 2 plus aqueous plus 1 permanganate plus 8 hydrogens. We know the electrons and the electrons are going to cancel, that it's, it's 5 and 5, okay? And now I have 5 iron 3, let's write that again, 5 iron 3 plus aqueous plus, let's see where we're at, 1 manganese cation plus 4 H2Os, and water is always a liquid unless it's a solid or a gas. And so now everything should be completely balanced in this thing. Right? We've got 5 irons and 5 irons. We've got 1 manganese and 1 manganese. I've got 4 oxygens and 4 oxygens and 8 hydrogens and 8 hydrogens. Well, what about the charges? Okay. Well, look, 5 times 3 is 15 plus 2 is 17 plus on that side. Do we have 17 plus on the other side? I hope so. We've got 5 times 2 is 10. Plus 8 is 18 minus 1. Hallelujah. 17 and 17. So it's balanced. Shoo-wee. Okay. This was a harder one. All right? For sure, this was a harder one. Be able to do it. All right? Be able to do it. Okay? Lots of practice in the book, and there's some problems like this on your homework too. Okay? So, what's happening with this thing here? So why is it that we had to have acidic conditions for this particular redox reaction? Okay? Well, as it turns out, you can't just go and combine any redox reaction and get a reaction out of it. All right, let me say that again. You can't combine any oxidation reaction with any reduction reaction and expect it to go. That's just not how chemistry works. Okay? So there's a list, there's something that we call the activity series. Some of you have been asking me about this. When are we going to get to the activity series? Here it is, okay? And I'm not going to spend a whole lot of time with this. You do not have to memorize the activity series. If there are any questions about the activity series, like in an exam or something, you'll have the activity series to reference. And so what does this mean? What does the activity series mean for us? Okay. Well, look, first I want you to note all of these reactions are written as oxidations, right? We see that? They're all written as electrons, as products. So electrons are being lost, right? Oil rig, oxidation is loss. So now there's 3 points to keep in mind from this, okay? A metal, so a metal cation, I'm going to box that. A metal cation on the list will oxidize any metal above it in the activity series. That's the same thing as saying a metal, not a metal cation, but a metal will be oxidized by any cation below it. Okay, so let's do this first example. Okay, lithium solid. A metal, so we're picking on metal, will be oxidized by any cation below it. So what does this mean for a reaction? Well, this means I can't combine lithium solid and potassium solid and get a reaction. But I can combine lithium solid and K plus aqueous, and I will get a reaction. And what's the reaction going to be? Well, it's got to be lithium plus aqueous plus potassium solid metal. Okay? But I could not write this reaction the other way. In other words, if I now write, let's see here. If I write lithium plus K solid, so I'm basically writing this reaction in reverse. That is no bueno. I want to put a big X through it, okay? So that's what these two points are. They mean the same thing. It's just two different ways of saying it, okay? So a metal cation on the list will oxidize any metal above it. So look, when I said lithium plus, there's nothing above lithium plus. Lithium plus can't oxidize anything, okay? But what about saying it the other way? A metal will be oxidized by any cation below it. Well, look, this means every single one of these cations could oxidize lithium metal. Okay, so that's what that means, all right? So now, why acid? Okay, right? In this problem, we had to have acidic conditions for this thing to go. And I haven't shown you the activity series of permanganate just with iron, but essentially what the reason for having to include acid in some particular redox reactions is because now if you look at this right here, any metal, so remember the metal in this table, those are all the things on the left, all the reactants. They're not the cations, the metal. Any metal below hydrogen will not react with H+. So it's the same thing we set up here. It is. It's really the same thing. It's saying that any metal below, right, any metal below will not react with H+. Okay, it's just like saying the K solid cannot react with the lithium plus, okay? But the reverse is true. So why is this important? Well, this is important because, for one, there's a whole bunch of other stuff that's not on this list, such as permanganate, okay? And for that matter, is iron on this list? Oh, there's iron, and you can see iron is actually above, okay? However, when coupled with permanganate, that's why it needed the acid, because permanganate's not on this list. So apologies for that. But another cool observation of this is, look, I'm going to point out silver, copper, and gold. My wedding ring, it's got silver in it, and copper. It's actually an alloy. It's a copper-silver alloy. I could take this thing. I wish I had a big bucket of acid right now. Not the stuff you take at Burning Man. I could drop this into a giant vat of strong acid. Nothing will happen to it. If I had a giant vat of strong acid right here, I would do it. I would drop my wedding ring right in there because I trust the chemistry. It will not react with it. And that's why we make jewelry with silver and gold, right? You'd be really bummed out if you spent several $100s on a gold ring and then it got oxidized by some acid. Not cool. Well, what about the copper? Well, we make pipes to deliver water out of copper. And that water can get acidified, okay? And if those copper pipes were corroded by acid, that'd be a really bad thing for all of our public utilities. So that's why we make these pipes out of copper. That's one of the reasons why we make these pipes out of copper. Okay, same, you notice platinum is on the list too. Mercury is on the list. So this activity series is pretty cool. It's a pretty cool predictive way of predicting what's going to react with what. So you do not have to memorize this list, but I do want you to recognize, if you were given the activity list, recognize that I can go from metal to cation down the list, but I can't go from cation to metal. Okay, and so anything below the hydrogen on this list means it will not react with the H+. Okay, so I'm going to move